Okay, thank you for joining back. So we are going to move on to the second method. And like I told you when we started, the methods we are considering for this class is the open method. The open method for finding the root of an equation. So the open methods are methods, like I said, they are methods in which you are just giving one guess. So remember last week we were giving two guesses and you need to find in which you know that the root is between those two guesses. Then you're going to find where the root is. But in the open method, you're just giving one guess. And in the case where you are giving two guesses, the guesses you are giving don't approximate, don't is not necessarily, the root is not necessarily in between those two values. So we are going to be looking at that later. So the Newton-Raphson method is the most popular method for finding the root, and it's popular because it's very fast. It's very fast, and it's faster than the other method. So in the Newton-Raphson method, you are giving an initial guess. You're giving an initial guess. Then you're going to find the next value. Remember for the previous method, the fixed point iteration method, you're going to get this, you're going to turn the equation, any equation you are giving, you are going to turn it into this form. So the next value is going to be given as a function of another function, which depends on the question. In the Newton-Raphson method, you're going to, the next value, the next value is given by this, the next value of the root. You are going to specify it by this approximation. So now, if you draw a tangent, if this was the value of the initial guess you are giving, if you draw a tangent to that, particular function, the point at which the tangent touches the x-axis is the next value of the root. So that's the basic idea of the Newton-Raphson method. So you are simply, this is the estimate, this is the initial guess you are giving. So in order to get the next iteration, just draw a tangent line to that particular value of the function. Then the point at which the tangent line touches the x-axis, that's the new value of the root. So in order to do that, you are going to use this geometric interpretation. So the difference between this point and this point is fxi. So this fxi and this 0. So this is the difference. Then the difference between this point and this point is xi minus xs minus xi plus 1. So using this relation, you say that the tangent or the slope of the line is equal to the change in y and the change in x. So this is the change in y and this is the change in x. So you say that the slope, which is the first derivative, is equal to the change in y divided by the change in x. You can also use Taylor's series to approximate, to get to this point. So we did Taylor's series in the second class, but you're just saying that the slope of the line is equal to the change in x, the change in y, sorry, divided by the change in x. So if you make this the subject of formula, you are going to arrive at, if you make from this equation, if you make this the subject of formula, or this the subject of formula, you are going to arrive at this. So the way you approximate the the next the next value of x for the next iteration is this. This is the formula you are going to use. Then this formula is the function. This is the value of the function. Then this is the first derivative. So simply, the Newton-Raphson method says that the current value of the root is equal to the present value minus dividing the value of the function at the current value, then the first derivative of the value of the function at the previous approximation divided by the first derivative of the function at the previous value. So let's do an example so that we can understand better. So I think there's a question. Okay. Please come again. I didn't get you. Let me come again. The Newton-Raphson method for finding the root, like I said, is the most common method because of it's very, very fast. It's faster than the other method. So you want to, the blue curve is the function you want to calculate the roots of. This is the blue curve. This is the true root. Like I told you, the point at which the function touches the x-axis, that's the root of the function. So this is the true root of the function. But in the Newton-Raphson method, you approximate the root by, for the Newton-Raphson method, you are going to be given an initial guess. So let's say that this point where my cursor is the initial guess. So you're going to draw a tangent line. You're going to draw a tangent line at that point. So the point at which that tangent line touches the x-axis is the approximated root of the equation. So yeah, we're drawing a tangent line. It touched the x-axis here. So that means that this is the calculated root of the function at that iteration. So you keep on going to the next iteration and you keep on going like that. So the way we derived the Newton-Raphson formula is that using this figure, the tangent or the slope is given by the change in y divided by the change in x. So the change in y is fxi minus 0, because at this point is fxi, then at this point is 0. So this is the change in y, then this is the change in x. Just subtract this from this and you get the change in x. So the Newton-Raphson method builds from this. So the first derivative or the slope is equal to the change in x divided by the change in y. Then if you make this the subject of formula, so this is the approximated root. If you make this the subject of formula, you are going to arrive at this equation where this is the function, at xi. Then this is the first derivative of the function at xi. So we're going to use an example so you understand, but this is the formula. This is the formula we are using for the Newton-Raphson method. So let's do the same example. So this was the example we started with in this class. So we want to use the Newton-Raphson method to approximate the root. Like you can see from the equation, you need to find the first derivative of the function. So this is the function here. So the first derivative of this is given by this. So you differentiate this, then you differentiate this, you get this. So once you've gotten the first derivative, you just substitute back into the Newton-Raphson formula. So this is the Newton-Raphson formula. Then this is the function which you are given in the question, and this is the the denominator is the first derivative. So once you've gotten this, then everything becomes easy. You start with the initial guess x0 is equal to 0. So this is the initial guess at the 0th iteration. To move on to the next iteration, so the next iteration is x1. So x1 is equal to x naught. Remember you are using this formula, x naught, that's the previous value of x. Then this at the previous value of x. And if you substitute x naught is equal to 0, if you substitute it here, the result is 0.5. Then you move on to the next iteration, which is x2. So x2 is equal to x1 minus this. So you evaluate this at x1. And remember, we've gotten x1 here at 0.5. So all you need to do is to put 0.5 here. You put 0.5 here, you put 0.5 here, you put 0.5 here. Then you get the new estimate of the root. In the next iteration, this is the formula. So you are at the third iteration. So all the other parameters is going to be at x2. And we knew x2 from the previous iteration at 0.5663. So you just substitute the values of x2 into this, you get the new value. For x4, you're going to do the same thing. You have a new equation, then you substitute the value of x3, which you got previously, into this, then you get the new estimate of the root. So you keep on going on and on like that. So I decided to stop at the 10th iteration. Then, like we normally do, we need to keep track of the estimated error and the true error. So we know the true error, we know the true root, the true value. So you're going to keep track of the true error. So if you look at this carefully, when we got to the second iteration, our true error was 0.1%. But in the previous method, the previous method we used, let me go back to that previous method. So it was even at the 10th iteration, we're still having an error of 0.3 for this simple fixed point iteration. It was at the 10th iteration, we are having an error of 0.4 approximately. But here, for the Newton-Raphson method, just when we got to the second iteration, just at the second iteration, we had an error of 0.1. So the Newton-Raphson method is very, very fast. So it's like the most common method that is normally used worldwide to approximate the root of an equation. And the reason is that it's very, very fast. So like I said, at the second iteration, when we tracked the true error, we got a very, very small error. And so if you keep on going, like we are still very, very accurate, because the value of the root we are getting is the same throughout. So the Newton-Raphson method is very, very fast, and it is very efficient. But there are some instances when the Newton-Raphson method may not work well. So we are going to emphasize that in the next example. So we have this function here, x raised to the power 10 minus 1. We are given this initial guess, and we are asked to find the root using the Newton-Raphson method. Like I told you, in order to get the Newton-Raphson method, in order to use it, you need to have the first derivative. So this is the equation. So the first derivative, you just differentiate this. You're going to get this. Then that means that the Newton-Raphson method reduces to this. So this is the Newton-Raphson method. So for different equation, for different questions, the working equation that you're going to be using for the Newton's method is going to be different. Like for this example, this was the equation we arrived at, and this is what we are going to be working with. Then for the previous question, this is the working equation. This is the equation you're going to use. Okay, this is the equation. This is the working equation. So it depends on the question. The, the equation you're going to arrive at the end of the day is going to be different. So you're going to use this equation now to find the next estimate of the root. So this is the initial guess. You're just giving one value. So this is the initial guess. So at the first iteration, the equation becomes this. Then you're having x naught here, you're having x naught here, and you're having x naught here. So you know x naught from the previous iteration, which is 0.5. So 0.5 will be here, 0.5 will be here. So you calculate the, the next value of the root. For the second iteration, so you have x1 here. So you know x1 from the previous value, which is 51.65. So you just put it into here, and you get the new value. For the third iteration, you just continue like that. And you're going to keep track of the estimate error and the true error. So we know the true value. The true value is 1. So we can get the true error. But in a case where you are not giving the true error, the true values, just ignore this in case you're not giving. So no need to calculate the true error. So if we look at this carefully, it's at the first, at the zeroth iteration, the error is 50%. At the first iteration is 5,000%. It's like 4,500%. Like this is blowing up. The error is increasing rapidly, is unstable. If you're going to go with the control term, it's very unstable, it's increasing. Normally the error is supposed to decrease as you are moving through the next iteration. The true value is 1. So you just compare 1 with 51.65, it's very much. So this the conclusion of all this is that the Newton-Raphson method is very fast, is very, very efficient, but it could be unstable. And the reason why it's unstable is because it's the true value of the root is not converging, and is diverging. And the reason why it's diverging is because the initial guess, the conclusion of the Newton-Raphson method is that the Newton-Raphson method is like the best method. It's very good, it's very fast, it's very efficient. But it depends on the value of the initial guess you're giving. If the initial guess you are giving is very bad, it's going to behave like this. Like the error is is increasing at an alarming rate and is not behaving properly. But if you are giving a good initial guess, it's going to convert, it's going to give you the value of the roots at a very, very fast pace. Like the previous example, at the second iteration, we got an error of 0.1%. But here, we are not having the same thing because it's because of this initial guess is not so good. So that's why we are getting that. But at the same time, the Newton-Raphson method is going to converge. Though now, at the 10th iteration, let me go to the 10th iteration. So at the 10th iteration, you are still having a very, very large error of 1,900%, which is very, very large. But then is still going to converge. If I had kept on and I've gone to the 11th, 12th, 13th, 14th, 15th, if I had continued with the iteration, at the end of the day, it's still going to converge to the true root. And I told you that the true root is 1. The true root is 1. So because of the Newton-Raphson method is very good, but because of it can behave tricky, like in this equation, in this question, it can behave difficult at times. So we need to be able to use a computer program, because I'm telling you now that if you move on, if you keep going, 11, 12, 13, 14, 15, probably when you get to infinity, that's when you are going to get the true root. So you cannot keep doing that by hand because it's going to be very tedious. So you need a computer program to do that. So for this reason, we want to write a computer program that is going to evaluate the root using the Newton-Raphson method. And this method is just the same thing with the previous method, the fixed point iteration. The only difference is just this line. It's just this line. Just look at this line carefully. And what this line is that the next value of the root is equal to the previous value, then f of x. That's this is the um, this is the function at the previous value, then this is the first derivative. So let me take you back to the equation. So this is the equation for the Newton-Raphson method. So the new value of the root is equal to the previous value minus, you evaluate the function at this value of x, at the previous value of x, then you do the first derivative, then you evaluate the first derivative at the previous value of x. So look at this equation carefully. So this equation here is just simply what you have here, but now this is in programming form. So the new value of the root is equal to the previous value of the root, x r root. Then you evaluate the function at the previous value. Then this is the first derivative function at the previous value. If you compare the fixed point iteration with the Newton-Raphson equation, this is just the line. This is the difference. This is the just everything is still the same thing. It's just this line that is different, and you need to calculate f of x. You need to calculate f of x, then you need to calculate the first derivative. This is f of x, and this is the first derivative. So this is the function that calculates f of x. And this f of x is simply the question you are giving. So remember, the question is that f of x is equal to x raised to the power 10 minus 1. Then you need to calculate the first derivative. Remember, if you differentiate this function, you are going to get this. So this is the value of the function, and this is its first derivative. This is the value of the function, and this is the first derivative. I think there is a question. Does that mean if the initial guess is greater than 0, the true error will converge slowly? The true error will be large. Okay, Joan Paul. Okay, thank you for that comment. It's not that if the true value, if the initial guess is greater than 0, it's if you are not, if the true, if the initial guess is not, if it's not so good, or if it's not so great. So you could, the initial guess could be anything, but if the Newton-Raphson method, if it converges very quickly, that means that your initial guess was very good. you had a very great initial guess. But if it is blowing up, if it's becoming unstable like this, that is increasing at an alarming rate, that means that the initial guess is not good. And that means that probably you should change the initial guess so that it can be faster. And if you cannot change the initial guess, that means that you need to write a program to help you calculate the root. Because even though it's very unstable, uh, if the initial guess is not good, at the end of the day, at if you keep on, maybe at the 40th or the 50th iteration, it's still going to give you the true value of the root. If you keep on going further and further and further, it's still going to give you the true value of the root. So what it's just telling you is that the Newton-Raphson method is good, is great, but in cases where it's misbehaving, you cannot continue using your hand to get the true value of the root. You have to use a computer program. You know, computer program can, when we are setting the maximum number of iteration, like when we are calling it and we set I max, most times we specify I max as 100. So this is simply saying that the Newton-Raphson method is very good, but then in cases where it's misbehaving, it's just better to use a computer program so that computer program can go up to 1,000 or 1,000,000 iterations. So at the end of the day, you're still going to find the true value of the root. So let me continue. So like I said, okay, another question. Is there not a code that does the derivative for us without inputting the derivative ourselves? That's a very great question. That's a very, very good question. And is it's it's because of there is a you can search for a function that does the derivative for you instead of you having to do the derivative yourself. But in this case, you have to do the derivative yourself, and you're going to write a function that is specifying the derivative of f of x. And the reason why I'm saying that your question is very good is that it's because of this is because of the highlighted reason that you've just stated. Like you rightly said, let me go back, you have to do the first derivative. And it's because of this limitation, that's why we have another method called the secant method. Because of you have to do the derivative. So another method was developed in order to bypass the derivative, and that's the secant method. So you're going to be considering the secant method. So you actually move faster than this than the space as which we are going. So the secant method is exactly like the Newton-Raphson method, like we'll be considering. The only thing is that you don't have to expressly calculate the first derivative yourself. So we are going to, that's the next, after the Newton-Raphson method is the secant method. So thank you for that question. But let's continue with this. So you have to, this is the function, and this is the question, and this is the first derivative. So you have to calculate the first derivative yourself and express it as a function. So this is the function at the previous value of the root, and this is the first derivative. So let me go back to Visual Basic, Visual Basic, so that we're going to try it out. Sure, okay. So we are in Visual Basic Excel. So this is the Newton-Raphson method. It's taking two parameters. So the first parameter is the initial guess. The second is the estimated root. is the error estimate. So you don't want the error to go to be below this. So you are going to be, this one is going to be specified, or you're going to change it depending on the value you got. So this is the estimated error. So if the current error is less than this estimate that you put here, then you just stop. And this is the maximum number of iterations you want to go. Okay, there is a question. Can you increase the size? Oh, okay. Let me increase the size. So, okay, this is better. Okay. All right. So this is the function. This is the Newton-Raphson's function. Then for the question, this is the value of the function. Then this is the first derivative. So let's go back to another question. All right. So let's go back to the Excel worksheet. So we've already defined the function. So we just call it in Excel worksheet. Let me go back to Excel worksheet. Okay. So I'm now in Excel worksheet here. So I specified the initial guess as 0.5, which is the same thing we had in the question. The error estimate for now, let me just put it as 0.01. Then the maximum number of iteration, um, let me put it as 100. So when I call the Newton-Raphson method, if you call the Newton-Raphson method using this, you're going to get this. I remember that 1 is the value of the true value of the root. So this was when we were doing it by hand. The error was escalating. But when we use the computer program, you're just saying that, here when we started, the error is like 5,000%. But now you are saying that you don't want the error to be above 0.01. So what the function is going to do is that it's going to keep on iterating until this condition is satisfied, or until this condition is satisfied. So you can use the Newton-Raphson method in order to do that. But in order to show you at which iteration the Newton-Raphson method converge, let me create. Here is just to specify the iteration. I want to be sure at what iteration. When we got to the third iteration, our error was like 1,900%. So I want to know exactly at what iteration you were able to get to the true value of the root. So let me say 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. I'll stop at 45, 41, 42, 43, 44, 45. Okay, let me stop here. The reason why I'm doing this is that I want to tell you at which iteration you were able to get this value, because when we are at the 10th iteration, the error is still very, very large. So I want to, so in order to, so the initial the initial guess is 0.5. So in place of I max, let me put F1. F1. Okay. So at the first iteration, this is the value is given. So let me go down. Then at 45. So can you see how it's going? So this was our first iteration. We got 51.65. This is the second iteration. This is the third, fourth, fifth. So, when we got to the 10th iteration, we had 20. We had 20 here. But if you had kept on going, it's going to keep reducing. Then at the 42nd iteration, we arrived at the true value of the root. So we eventually got to the true value of the root. So what I'm just saying is that the Newton-Raphson method is very, very good. It's very efficient. But if it's not working as you would expect it to do, just write a computer program, which we did, the Newton-Raphson's function, so that the computer can do it for you, and you're going to arrive at eventually. But we cannot go to the 45th iteration by hand. So it's not advisable, but a computer program can go very, very fast, and you can get to the true value of the root. So we are going to go to the last method, which is the secant method. And like I hinted, the secant method is just the same thing like the Newton-Raphson method. It's just that you don't want to calculate the first derivative, like the question John asked. He pointed out that is there not a way to go about it instead of having to calculate the first derivative of the function? So the secant method is going to account for that. So I'm ending the meeting now.